chalk that we've gotten is just inferior.
If you break that piece of wood chalk, you'll have two pieces.
Okay, let's get going. Today, we are going to continue on with streams that we saw at the beginning of this morning, or the beginning of today. I'm going to give you a bit of overview and maybe some insight into exactly what streams are good for, why we have them, why it's an interesting concept, and why it's really not that big a deal. Then we're going to talk about tables and give you a brief implementation of tables. And we're really doing tables only so that we can do memoization. I'm going to just blast through tables because you all should be able to figure out how it works at this point, so that we can do memoization. And I'm warning you now, the memoization is going to be dull and dry because we're going to do a full-blown environment diagram on it, just so you know. Okay, now, here's the good news. The good news is we've gotten to the part of the course that we've been waiting to teach you for 3 weeks. This stuff is all so cool. We're very excited about this. Streams, it's just a fantastic idea. Streams are, in effect, taking the concepts that we've learned about recursion and process and so forth and converting them into a data structure. Whereas we had a recursive definition of functions before, which everybody has gotten a good handle on at this point, we are now going to take that idea and apply it to data structures. And I'll talk a little bit more about that in a second. The next thing that we're going to be doing is the metacircular evaluator, which is just so cool. It's going to be great. It's going to be hard because, as you remember when we were doing the pattern matcher, there are 3 levels that you have to think about simultaneously. There are 3 levels you have to think about simultaneously, but you've seen that once before, and hopefully that will help you figure out when we get to the metacircular evaluator exactly what's going on. And then the last part of the course, this week is just a great week. The last part of the course, we're going to talk about compilation and give you a very, very brief introduction to that. Compilation normally takes a full term, if not a year. So this will be necessarily brief. Unfortunately, this is the only time that you will see compilation this year. I'm sorry to say. That's the way the curriculum has been organized. But we will attempt to do our best at that. But it's all very near and dear to my heart, at least. And I know that Holly enjoys working with it and teaching it as well. So this should be an exciting week for, I hope, everybody, at least for us. So let's get back to streams. Streams are useful. I want to place them in context. Why do we want to use streams? Why do we have streams at all? Streams are useful because we have oftentimes extremely long data sets, which are sequences of numbers. Long enough that they cannot either readily be stored or readily be computed, or that the computational overhead to create additional elements of the streams of this long sequence of data is very, very high. When might this occur? Say, for example, you wanted to simulate the weather. Very, very high overhead to do that. You don't want to sit down and write down all the numbers out, especially since you may be simulating for years and years and years. You may not have the capacity to do that in your computer system. But as you're writing down these numbers, you notice that there are patterns. For example, let me make up an example. Over here, you're watching the weather and you realize whenever there's a storm in New York at this point in time, there's a storm in Boston. And whenever at this point in time it's clear in New York, at this point in time, slightly later, it's clear in Boston. So if you can record the weather in New York, it will help you predict so that this makes a little bit of sense in a second. What you've done with a Turing machine is expressed a very long sequence on a tape in a condensed form. Okay. Now, for the rest of you who haven't heard about Turing machines, you will hear about them in a couple months, and you'll understand what I was talking about just then. You'll say, oh, right, of course, they're like streams, okay. Now, what was I talking about? Let me give you just a quick little nugget of explanation. In a Turing machine, there are two parts. There's a tape, which is a sequence of symbols, which will be our stream of numbers. And there is a small machine, which will be our program. And as the machine is run on the tape, it mutates the tape, takes it from one state to another, which is very much like what we're seeing with the streams and our stream operators. We generate an initial stream, like ones, and we use a stream operator to create another stream, like the ascending integers that we saw earlier this morning. Now, again, in a couple months, you will see that again, and you'll say, oh, yes, you'll have deep insight. At least I hope you will. So, streams can also be used to describe, as an elegant way to describe the behavior of a system over time. Excuse me. And oftentimes, engineers use them to describe systems that can be very succinctly explained. So, for example, if you have a tuning fork and you strike it, it emits a sound. Before you struck it, it emitted no sound. But still, whether it's emitting sound or not, the physics of the tuning fork are the same, such that if it flexes outwards, it flexes back inwards slightly, and goes on and on like this for a very, very, very long time. And that's really all it does. But you have to strike it. You have to give it initial energy. If it's flexed outwards, though, it will then flex inwards. And if it's flexed inwards, it will then flex outwards. And those are the complete rules of a tuning fork, to very coarse approximation. So what does that look like? Well, say we have, over time, the input to our tuning fork. And say at time 0, I give it a whack. I'm going to represent that with that symbol. So at time 0, I whack the tuning fork. That's the input. Here's the output. Let me make sure I get this right. So whacking the tuning fork causes, say, the tines to swing inwards. The next time we look at it, the tines will be swung outwards. So a little bit after this, the tines will swing outwards. And then, because they're swung out, they will begin to swing inwards. And then, because they're swung in, they will then swing outwards, and so forth, like this. Now, the diagram I'm drawing like this may be a little unfamiliar to you, but perhaps something like this would be more familiar, where we have an oscillating signal, like that.
It's going to decrease over time.
It will, in fact, decrease over time, but we're going to ignore that for right now. These dots, which I'll draw in orange, are an approximation to the underlying sinusoidal wave that we would expect to find out of a tuning fork. If you don't have deep understanding of what I'm just saying, I hope that the simpler explanation will provide you with some basis for understanding this. So we hit it, it then responds. Because it's responding, and the description of the system is such that it alternates states, we get an oscillation despite the fact that there's nothing that occurs after that on the input. If you consider this to be a sequence of values, here this is the value 1, whoops, wrong color. This is the value 1, and elsewhere it's the value 0. And this is the value 0, or minus 1 and 1. Don't express it. The underlying essence, the physics behind what's going on is here. This is what we want to concisely express, not this which perforce must be infinite. That's why we use streams, because streams allow us to express this sort of structure in a very concise form, because we're explaining how to compute the results, not what the results are. In the same way, when we write a program, we're describing how to compute the results rather than what the results are. Except this time we're going to fold the recursive nature into, like the recursive nature here, into the data structure rather than having it be part of the program. So if we were to express this as a stream, oops, this is the way it would be. Here's the input stream. This is going to be cons stream of 0 onto cons stream of 1 onto the stream of zeros, which we saw earlier. 2, 3. The stream of zeros that we saw earlier this morning, which is an infinite stream of just zeros. So you see this generates what I just erased here, the 0, a single 1, and then zeros. And we want to compute the output. That will be as follows. The stream out will be now you might ask why I'm doing cons stream of 0 there. I'll get to that in a second. That's supposed to be just an argument. There. So what does this do? We need to represent that there has been no input for a very long time, and that has generated no output. So we're cheating a little bit by defining the first element of the output to be 0. But after that, we just scale the sum of the input and output. This gets delayed once, because of the inherent delay in constructing the stream. This expression gets delayed once, which is what we see down there. The scale stream is multiplied by -1, and the add stream is the adder up at the front. And if you run this, what you get is exactly that sequence. 0, -1, +1, -1, +1, and so forth. Actually, 2 zeros first. This is the equivalent of that. And that's why we use streams. Things like that. Clear?
Where's the delay coming in? Scale stream?
Because we have cons stream, therefore, this part is delayed. Both in the sense that this word is delay, that we wait one time step, and in the sense that we implement that with the delayed operator, or delay operator, as cons stream is desugared.
Would one look into the internal stream manipulator, scale stream and add stream, to determine that there weren't any delays inherent in them through a specific cons stream operation? The scale stream is immediate, right? No delay.
Immediate in the sense that when you call this, you get the next stream element. But it doesn't scale the entire stream right away.
Right.
There's always a delay. So the secondary idea here is that in a stream you have, you have two elements to a stream. The first element is the constructed value. And the second element is a procedure to construct the rest of them. So this is equivalent, or this here, is that, and this is that. So we have an element or perhaps a series of pre-existing elements, at the tail of which is the process to generate the rest of them. It's like a list, except that we've abbreviated it. And we've said, well, we're not going to give you the rest of it. We'll just make it when we need it. Not unlike a Taylor series expansion, where you have all of the expansion terms beforehand, plus the error term at the end, which, if you wanted to, you have the mechanism to generate additional terms out. Okay. So much for streams.
But the procedure may not exist.
I don't understand.
You are, in this case, giving me a formula.
This creates a procedure.
Right. So the procedure may not exist. The procedure may simply be a long string of numbers.
Now, the procedure is going to be a mechanism to generate the numbers. If you have previously generated them, then they will exist. In a sense, they will exist. And we'll see what I mean by that. If you have not previously generated them, then it's a formula that you need to compute the particular element you want. It's going to be, in effect, a condensation of an infinite stream that continues off.
If the condensation exists.
If we can write it down like this.
Right.
It,
If it doesn't, though, then we can't actually use this.
yes. This isn't something that gets generated automatically. That's one of the concerns. This is something that comes directly out of what we write down. Okay. So, yes?
So if you can't represent it in a closed form to sort of generate a function, then you don't use strings in that sense because
So,
it used to be raw data sitting in memory already.
right. The question is, can we, if we don't know how to generate it in nice, succinct closed form, we can't use this. And the answer is yes. That's right. We have to be able to write down some analytic expression of the generative mechanism. Otherwise, we can't use this. Okay. So, for example, you couldn't use this to really create random numbers. You wouldn't want to because there's no history to random numbers.
Well, I mean,
No, I take that back. That was a bad example. I take that back.
Yeah, not that, but even in the other case, you can use it, but it's really doesn't have any value.
It doesn't have any value, right?
You could use it as a pointer to an address already that stored that
Yes.
information, but it doesn't add any value.
It doesn't add any value. Yeah.
You're pointing to a string.
You're pointing to a stream.
You're equating the third term to 17 and the fourth term to 23. You have no formula, so you're pointing to
Yes.
a chart that
Yes.
defines. In which case you already basically have a list.
Right. In which case you've devolved into a list. So let's take a look now at tables. Before I do that, actually, let me just make sure. I'm going to repeat something that was said earlier today, just because it's important, and I think that you understand, but I want to make absolutely sure. A stream is a list, and I sort of alluded to it in this diagram right here. Oops. Let me do that properly. So we have some list L that has value A1, A2, and a mechanism to generate A sub I. And when we create this part, it may be a self-referential explanation. And the only reason that this doesn't just bomb is that we're delaying the execution of this. We're postponing this until it's needed.
For the things we've already generated. Did this data structure come with lists? Is that really what it's got?
No.
No?
No. Although it was early. There was an early development of it that included Lisp. They included Lisp. There is an explanatory footnote in the text that goes through some of the history.
So absolutely correct.
Yeah, it's quite clever. It is. Right. So this is no. That's very true. I mean, it's clever because this is the embodiment of a higher structure that we're observing that will generate these values. This is a much more powerful mechanism than just writing down the numbers.
It would still be a tree to have the additional right?
Yes, this is just to indicate that it can have any number of finite elements beforehand. It's just the big difference between a list and a stream is that the final element of a list is nil, whereas the final element of a stream may not exist, and the final element of the extant terms of a stream is a procedure to create the rest of them. And notice I said actually procedure here. It really is. It's going to be a procedure. It's going to be usually a procedure of 0 arguments, a func, as we call that, that we will execute to generate the next element or the element after that, what have you.
So the empty stream will only be used if we're pretty much only if we're combining a non-infinite stream with a
Finite streams, right? Right.
We're almost never really going to work
Yes.
with finite streams.
Yes. Okay. So let's do something that's much more mundane, come out of computer science. And you'll see this kind of idea, perhaps it's not come out of computer science, but it's best expressed within the guise of computer science. You'll see it in Turing machines and computability. You'll see it in signal processing. It's really a very, very nice expression of it. So much more mundane tables. And I really don't want that chalk. Let's try this one. Oh, yeah. Tables. Now, your handout today has 2 sheets on it. I'm going to tear them apart, but please don't unless you really care to. Don't do it just because I did it. The second page is the table abstraction, which we'll go through. We're going to use that then on the first page to hammer through this environment diagram. When we hammer through the environment diagram, I hope you will therefore understand memoization and see why it's a really good idea. I'll give you some intuition before we actually get to it. But first I want to go through how tables work, or how tables work in this particular implementation. So we will have, of course, this is a new data abstraction. We will have a constructor, a selector, and a new feature, a mutator. We previously haven't seen mutators because we have not been using mutator functions, special forms, like setBang and setCarbang and setCouldrBang. Now that we have those, now that we have the access to those, we're going to start taking a look at, for example, the queues that we saw before, queues with mutation, and now tables, which are very similar, where we will be changing things in place. If you wanted to make, for example, a circular list, which relates to one of the challenges that I put up some time ago, you would use mutation to do that. Okay. So take a look at make table, which is our constructor. Let me just write it out. Make table returns an empty table, which will be just a list. Easy enough. We're going to be using a tagged list to hold our tables. When we want to look something up, that will be our selector. We will be looking things up like in a dictionary by a keyword. So there's the key, and we'll have to pass in the table. That will do something very straightforward and simple. It'll try to put a record, pull a record from the table using this function assoc, which we'll get to in a second. If assoc finds an entry within table, it'll return it. It'll return the entire record. We'll talk about what the data structure is inside the table. Otherwise, it'll return nil. So we want to check if, whoops, if the record exists, that is, if it's not nil, we want to return the cooter of the record. I'll explain in a second why we return the cooter of the record. Otherwise, we return false or nil. 2, 3. Yes?
Quick question. How come on our handout we have it as the footer of the table and the credit card is where it's search key for the table, and here we just have regular table?
Because I made a mistake. So the first question is, why do we have this cooter here? Why don't we have just table? Because our table is going to be a tagged list. The first element in the table is going to be the symbol table. And then we're going to have a series of records. Each record is going to be a cons cell, which on the car will have the key value, and the cooter will have the value, the associated value. Oh man, I really don't like that chalk. We've seen this structure before. It's very much like the tags. In fact, we're just going to be tagging any value with a particular key. We're going to be calling it, we're not going to be using the attach tag and tag and contents operators. We're going to be using slightly different ones, but it's basically the same idea. Yes?
You closed the let here?
I hope I didn't. This, no. If I did when I typed it in, that would be a mistake.
What's the star notation?
Star is just a symbol.
I mean, what is it used for tables? Is it used for tag data? Like what?
This is just a special symbol. We could make this just be a regular table. The reason we're using it here is to dissociate that from the entries within the table. So even though this is going to be a separate symbol here, and these are going to be separate records, this is still a list. And if we're not careful, these here, scratch if we're not careful. These here are also potentially lists, especially if the value is a list, right? So then this could be just a structure that is just a list, and the table could be confused with the key within a record. Does everybody see that? It's a little bit subtle. It could be, if we're not careful, this structure is really identical to the table structure. It's the same thing. We're just calling it different names. And to help prevent us from mistakenly taking this to be the key in one of the records, we'll give it a name with stars around it, which should set it off from our regular key values. Even though we probably won't ever search on that, we won't look for it and so forth.
Unless we wanted to make a table of tables.
Unless you want to make a table of tables, right? Sure. So that's why we have this coulter here, to skip over that first element, which will give us then just a list of entries in the table. Each entry is going to have a key, an association between a key and a value, and we'll be able to provide the keys and get the values back using this function assoc, which we'll write now.
John, each R sub 1, R sub 2
Yes.
is a pointer to a con.
Is one console, right? That just doesn't work. Bad chalk. Yes? A table is a list.
Are we indicators now, or are we is assoc still selector?
Assoc will be our selector. Well, it's I'm going to define it here. This is assoc that we're now going to define. God, that's just horrible. Assoc is going to take key and records, plural. If we're out of records, that means there was nothing to find, and we return false. If, on the other hand, we use equal. If the key is equal to the car, or car, of the records, close, we then return the car of the records. Why car and car?
Because that's the key, and that's the whole record.
Right.
What the record with the key?
This will return the record with the key.
Do we also need to check to make sure that we have a properly formed bunch of records so that we can take the car?
Ideally, we should. This is a rough and ready implementation.
Is the equal necessary?
Is the equal necessary, or can we just use EQ? It depends on how we're going to actually, what sort of things we're going to store. By using equal, we can store arbitrary structures as keys. And that will be important in a second. Or a few minutes once we get to memoization. Otherwise, we don't have a match, and we recurse. And we close the coulter, assoc, else, cont, define.
So this is really like a one-dimensional table?
This is a one-dimensional table. Yes, this is a one-dimensional table.
Two keys.
You could do that. You could, in fact, you could make an association on one key that would then return a new table, and then you would do a secondary lookup on the new table with a secondary key, and then you would get a two-dimensional or a double association mechanism. The order in which you specify the two keys would be important, though. So let's do one quick example here. Oh, no, sorry. We've got the mutator still. So we've done the constructor selector. Now we need the mutator. Define insert bang. Why insert bang? Because it mutates things. Insert, and this will do the following. Let record soc key table. Thank you. Cooter table, cooter, soc record. If the record is found, we first look up the record using the same mechanism we used before. If the record is found, we want to mutate the contents that are there. So we do set cooter bang record and value. Is it clear why that's going to work? A record is a pair. The car of the record is the key. The cooter of the record is a value that's getting associated with that key. So if we want to change the value associated with it, we find that pair and change the cooter. If we don't find the pair, if this test fails, we need to create a new pair and insert it into the table. So the insertion into the table happens here as a set cooter bang of table, and then a cons, which is the new association of, cons of the key and value, which is the new association, onto cooter of the table. 3, 4, 5, 6. I left the tag. This should leave that intact.
Oh,
Because we're going to set cooter
all right, sorry.
of the table. Remember, the table is the special symbol table along with a list of records. So we're going to leave the car of that alone. It'll still continue to be star table star. But we're going to change the cooter to be the cooter as it was with a new element constant to the front of it. So if I create a table that is inserting with keys that are in sequence 1, 2, 3, and 4, what order do they appear in the list? If you were to print out the table, what order would they appear in? 4, 3, 2, 1, right? Because they get inserted at the head of it. So let's do a quick example of that. Just to hammer it home. My life without chalk is just life with rare chalk. I didn't bring that. So we'll do define tab. Why am I not saying define T to be make table? Why am I using tab instead of T? T would seem to be an appropriate abbreviation for table. Because it looks way too much like sharp T, way too much. You should not use that. That should not be a symbol that you use. Suppose you have in the middle of one of your functions, you want to return true, and you mistype it as T instead of sharp T. Good luck finding that bug. Okay, so we define tab to be make table. What is tab going to be? Let's say at this point, here's tab. Let me use a different color though. Here's our table. After we define it to be make table, it will be the list star table star. If we now attempt a lookup of 1 tab, what is that going to return? Right. If I now do insert bang of 1 and A, what does table become? And then, sorry?
And then the console, one, it would be 1 dot.
You need to call your insert.
Oh, yes, I'm sorry. Yeah. And I should spell table correctly. So now if we do lookup of 1 and table, what will we get back? The symbol A. If we do an assoc of 1 and table, we would get 1.A. Because we're just doing lookup, or because we are doing lookup, not just assoc, we get A. Now if we do insert bang of 2 and B, whoops, drop the table again, on tab. What are we going to get? Let me write it down here. Star table, star. We said that things get added into in reverse order. So this will be 2.B and 1.A. Clear enough? Good. It's tables. Yep.
There's no restriction here at this point from us entering multiple items of the same key value, is there?
Yes, there is. If you remember, or if you look on your handout on insert bang, no, insert bang is up here still, right? So if we provide a key that already exists, this will pull back the record for that key here. If the record exists, then we'll just rebind the value.
Is the system of consoles and lists in fact how a commercial database, is that the underlying representation in commercial database programs?
This is so simplified that it couldn't possibly be true. Commercial database systems are very, very, very complex things, and I couldn't begin to tell you how they work in general, given this framework. There are many times you have effectively association lists, which is what this is. It's an association between a key and a value, but they're just very, very complex compared to this. Yes.
Part of that would be speed, right? And if we were, rather than just throwing them in order, if we arrange them alphabetically by tag or something.
Right. You might.
Like before we were talking about looking things up in the
Right. If you wanted to do things like have insertions become alphabetical, you might think about doing it here in insert. You might, if you have speed concerns, you could talk about ordering these in particular ways. It becomes very, very complicated if you have a large system. So let's finish this up and just say, do one of those modifications. Insert bang 2 to be C, as Brian was suggesting. What is it going to be now? I'm sorry to cross the board, but we need the room. What is it going to be? .C now, 1.A. Clear?
Have we defined a way in tables to delete anything?
No, we have not. This implementation does not have a mechanism for deleting entries. Okay, now that we have a good handle on tables, here's what I warned you about. Oh, sorry, one last thing. as was observed, these keys don't necessarily need to be a single value. Where is key used here? Everything that we've written down so far, and because of the equal predicate that we had up here, not EQ, but equal, we can put in arbitrary structures as keys. So if we wanted to make an association between a particular list or procedure or what have you and any other arbitrary value, we could. And that'll be important, not in the example I'm about to show you, but in this style of programming that we're about to see.
You ever actually figure out, determine what equal does with
Exactly the same, they should return T. In any other case, no, I'll take that back. I don't remember exactly what it does. But yeah,
might work.
it might work. Yes.
Can I just ask you quick,
Sure.
the difference between lookup and associate and why you use associate here? I mean, I'm not sure why you split up lookup from associate. You said
Right.
There's a hard word for lookup, but what's the...
We could have used lookup here.
Assoc is a native scheme thing.
Uh,
So that we just.
I don't believe it is a native scheme thing.
Oh, well,
Yeah.
AskQ is the EQ version, and there's AskV or AskV and Assoc, I think.
I'm not sure it's built in. I'm not sure it's primitive. I'm not 100% sure. We could have used lookup here.
Okay, is there something lookup gives you that associate doesn't? It's good addition. Okay.
So the reason, let me state this again. I misspoke. There is in fact a reason that we use assoc here, and not lookup. Does anybody know what it is?
We can't set clear of it if we don't have a pair.
As Heather was saying, it returns the entire record, and therefore, as Chris was saying, we can set cdr of the pair. We don't have the ability to set, if we just have the value that we want to change, not the place where it's being held. Remember, an association is a pair between a key and a value. We need to get our hands on this object here. Lookup will return only this part. And therefore, yes.
Go ahead.
And therefore, we won't be able to do this.
It is true that you could have written it all as one. I mean, you could have put all the
Yes.
intelligence of the associate into
Yes.
the lookup.
Sure, you could have. Yes. It's just it's a easier implementation.
I know
Yes.
earlier today Holly said you can't use setting with lists, but it's not clear to me if you did use lookup, why you wouldn't be able to set bang value to whatever.
So say this was lookup instead of assoc. I'll continue to use the yellow. And we used set bang instead of set cdr bang. This would say set bang record to value. So that would change record. Where is record defined?
Inside the function.
Right here. So that would change this value. It wouldn't change what you want to change.
Is there any way of changing record so that you're changing the right thing? No.
No, because we've lost our pointer back in the data structure.
We've lost the pointer back into the data structure. We don't have access to this part of the const cell anymore. What we have is this arrow here. And record is pointing there, so we have record over here. And let me do it. If we draw an environment diagram, which we're going to be doing a ton of in a second, we have record, and it is pointing, in the current case, to here. Or I should do that in yellow to indicate which case it is. And if we do set bang of record, we're going to merely change this and have it point somewhere else to the new value. Call it value prime. we need to be pointing to this one here to be able to change this link. Is that clear?
Yeah.
That's a subtle but important point. Okay. So now we're going to use tables to help explain memoization. So one of the features that streams allow you to do is to encode, as we said at the beginning, to encode the inherent structure of a sequence as a small procedure, which gives instructions on how to generate elements from that sequence. But suppose that procedure is computationally expensive. And suppose, further, that you're regenerating portions of the sequence repeatedly. There's no point in redoing what you've already done when the answer isn't going to change. You're just going to get the same value again and again and again every time you call for the third element of the sequence. So why repeat those computations if you don't have to? Provide some sort of short-circuiting mechanism that if you happen to ask for the third value of this stream, we'll just give it back to you rather than recomputing it, because it's going to be the same. If you happen to ask for the fourth value of the stream, we'll just give it to you right away rather than recomputing it. If you ask for the fifth value, it hasn't been done, please go compute it and make sure you tell us so that we can write it down for next time. And that mechanism is called memoization, because you're writing little memos or memorizing the previous values. And we'll make associations between the inputs, that is, a location on the stream, and the values that were returned. Or in general, in the general case, for any function, input values and the output that was produced. So that's why it was important that we could store any key into our table, because we're going to use these tables now to save the inputs to a given function and record the outputs that were generated. And now every time that we call a given function, we'll check. We'll compare the current inputs against the previous history of inputs and see if there's a value already there, recording it. If there is, we'll short-circuit the computation and return the value immediately. If there isn't, we'll allow the computation to continue and complete and snatch the value as it's being passed back and stored into the table. Notice that there is a very, very big assumption that I've made in why this could possibly work.
We always get the same value.
We always get the same value. Every time I ask for 3 factorial, it's always going to be 3 factorial, every single time I ask for it. That means these functions that we're using must be, these procedures rather, that we're using must be functional. They cannot have side effect. Otherwise, all bets are off. It's not going to behave the same way, because we'll short-circuit the computation which was side effecting. So for example, if your procedure has a print statement in it, every time you call your procedure on the value 3, without memoization, you'll get that print statement coming out every single time. With memoization, it'll only happen the first time. Every time after that, the result has been captured and the computation is short-circuited. Is that clear? This is another deep, deep idea that goes well beyond what I've just described. This is in general called caching, and you'll see a lot of it in 2 terms when you talk about machine architecture and how to design machines. And there is a deep, deep idea that once you do something, you're very likely to do it again. Once you've stepped foot in a particular area, you're likely to continue to be in that area. This idea of locality. Once you've asked for a particular value from a function, you're very likely to ask for that value again. And so you want to cache that value. hold it so that you can return it again quickly rather than going on and doing the full-blown computation. It's a very simple idea, but a very deep one that has huge, huge implications in the way we design machines and in the way we're about to design these processes. It will take, using memoization, it will take an exponential function, an exponential time function, into a linear time function. Huge savings.
Assuming your lookup is faster than calculation of the function, right?
Doesn't matter. Assuming our lookup is constant time,
What?
it could be a very long constant time, but as long as it's constant time, it will be faster than doing of an exponential. Now, chances are it won't be constant time. Chances are it'll be something like linear. Linear isn't so bad as compared to exponential.
Doesn't
Oh.
that defeat the whole notion of streams in terms of trading space for time? That is, you start by saying we don't want to save
Yes.
the entire stream.
Yes, so this is a very, very, very good observation, which seems like we're battling against ourselves. The example I'm about to do doesn't have a stream in it. But if we are making streams, then it seems like Baruch is saying we're battling against ourselves because we had this elegant way of expressing a condensed version of a sequence of numbers or values, what have you. And yet we're going to use it anyway, we're going to expand it anyway, and expand it out to its full breadth, and save them anyway. There are two things that are different. These are two slightly different things. Let me explain how they're slightly different. The one is a very elegant way to condense a stream, perhaps to no elements, or one initial element. Now, it could be that the one initial element isn't very useful, and in fact, we need the first 100 elements, and beyond that, we don't need it as much anymore. So we use the condensation. In which case, we really do want to have the full 100 first elements. The second case is where a given element, and this is what we'll see shortly, computing a given element requires having computed many, many, many previous elements, in which case those must all exist. And you can imagine now, if we want to compute the fifth element, and it depends on the four previous ones, then the next time we compute the sixth element, it requires the fifth and those previous. And if we're starting from scratch every time with a short list, we're repeating a huge, huge amount of computation. So that's another reason that we use memoization, these two somewhat orthogonal ideas.
In fact, if you limit the size of how much you stack of the table, then
No,
you allow?
no. I mean, in practice, no, you don't. You can, but in practice, you don't. Yes?
So what is the difference then between, I mean, we defined streams as a delayed list, so and I hope I'm not rehashing the same question, but I don't quite understand the difference between computing the value and storing it in a list, or computing the value in your stream when you need it, and then storing it back in a table, which is then also actually a list.
There really isn't any.
You only compute up to the highest number you've asked for.
Yes.
Right?
In both.
They're infinite streams, so
In both
it's
cases.
impossible to calculate them all on the list.
In both cases.
And if your needs change, you don't have to recompute the whole thing, you just pick up where you left off.
So on the first page of the handout, there is exercise 3.72 from page 272 of the text, which we will now go through in gory detail. We are asked at the bottom of the page to draw an environment diagram of the execution of memo fib 3. You remember Fibonacci fib, which computes the Fibonacci numbers. It's a doubly recursive exponential growth, time growth function, and we are going to short circuit it by using this memoize operator. We are going to create a table of values of previously computed elements, so that when we get to the 12th Fibonacci number, which is the sum of the 11th and the 10th, we will already have computed the 11th and the 10th values, and therefore we'll just pull them out of the table, rather than, as previously would have happened, compose a large computation into the 12th value. So let's take a look and see how this works. You have the code in front of you. I'm going to bravely try and over the span of the two boards, draw the environment diagram. If I don't make it back alive. So the first thing we have is the global environment. And within the global environment, there are two functions which, yes. First, there will be memoize, which, where is it? It's a let. Oh, sorry, there's a, it's a procedure of one argument f, and the body is a let statement. So far, so good. We then want to execute define memo fib. So there's memo fib. Which will be the call to memoize of that function lambda, and or that lambda expression. You notice the lambda expression has very similar structure to the fib, that's above it. The lambda function is, in fact, a memoized version of Fibonacci. And it's recursively defined. That's what we're going to try and do. So we define memo fib to be a call of memoize on a procedure. Memoize is a function. We have an application, therefore we create a new environment. We copy this pointer here. Make sure that I'm getting this the right way. This points to there. It has one argument f. This is memoize. And then one argument f is what gets evaluated on that lambda call. So in fact, it's just lambda. The argument, the environment is which environment? It's the global environment, because that lambda expression was evaluated as part of the application. That's the argument to memoize. And the body is, the procedure, parameters are n, and body is a cond. Wow, that wasn't so hard. Oh, but we're not done yet. Right, so we've defined memoize and memo fib. What did I just say? Wow, that wasn't so hard. Because all the computation's been delayed. Well, okay, well, we just did a definition. All right, modulo that. Let's try now, to run this. Oops, memo fib 3. What does that do? Application creates a new environment. Yes. Oh, yes, thank you. Memo fib will then point to, right. I completely did not complete. I did not finish that. Shame on me. It was way too easy, wasn't it? We didn't actually call memoize. I mean, we got the procedure we developed the argument and didn't pass it in. Sorry. So down to memoize, we create. It's in the body of memoize now to do the application, which I skipped. We create a table. We create a new frame because we have a let. Within the let, we define the symbol table. And table is a return for make table. I'm not going to do the table operations. It just gets way too hairy. We just assume that this now points to a list star table star. And then within memowise, we create another lambda expression. Parameters are x. Body is a let statement. Environment. Which environment is it? This one here. And where does the let points to? The let points to here, because it was created by memowise. Okay, so far so good. Is there anything more? Well, we have this return value now that we have to worry about. And where does that go? Right up here. And we're going to get over there, like this. There we go. Kind of bypassing everything, almost. Let me pass it a different way. So if you drew that, well, you probably did a better job than I did anyway. So let's pass it down through there.
I just wanted to kind of orient myself. Memowise is a function that just creates the table, basically.
Memowise, looking at the function, it creates a table using make table, which is what we just did here, and then the body of memowise is a lambda expression. So we've created the lambda expression, here it is, and returned it, and bound that to memofib in the statement above, in the expression above, where we have defined memofib to be memowise of that lambda. So far, so good? Okay, now is when I meant to say, well, we're done, because all the computation has been delayed. It's here. So now let's try memofib of 3. Right. First step, we create a frame for the application of memofib. And this, unfortunately, is getting too small to use. Which frame is that a copy of? What is it pointing to? Memofib. Memofib is here in the global environment. It points to this, in that winding path to that procedure. Therefore, this points to let. So I'm going to give that a name. Let's call that environment 1. That's E1. And within it, we have
parameter.
X. And the parameter is bound to 3. So far, so good. Within the body of this lambda, which is the lambda within memowise, we now have a let. Parent environment, right there. And within the let, we define previously computed value. I'm just going to abbreviate that to prev. And that is a call on lookup x in table. X is 3. Table is, well, where does table come from? It's not here. It's not here. Ah, it's here in E1. So it's this table. Table star. And that returns nil, false. Therefore, we look below, or previously computed result. That does not succeed. Therefore, we continue on. We have another let. Parent here, and within which we define result, which will be f on x. F is, where is f? F isn't here, it's not here, it's not here, it's not here. Way back here is f. This is why we have pointers to keep track of this. There's the procedure. Which procedure is that? That's the one in the call to the definition of memo fib with lambda of n. So now we apply that to, so this is the lambda of n, applied to x. X is much closer, it's 3. So looking at that now, lambda of n on 3 will be cond is 3, 0, no, is 3, 1, no. Otherwise, we now compute plus memo fib of n minus 1, which will be 2, and memo fib of n minus 2, which will be 1. Now I'm going to start numbering things. This will be the 0th call to memo fib. This will be the first call. And we'll continue on with that. We won't get to this one just yet because we're going to do this one first. Right? So far, so good. We have a lot of incompleted values here, but this is the way it's going. We now we have a call to memo fib. New frame. X is 2, parent frame E1, memo fib. What does that do again? Oh, that's right. It's this let down here inside. It got returned from memo-wise. It has, the lambda, so we have a let, same as above, with the previously computed result, which will be a lookup in table. Which table will it be? Same table as before. That's the important thing. We're always referring back to the same table in each of these calls. So we do a lookup of 2. What will table be? Star table star, because we've done nothing to it. It'll still be empty. So we'll still get a nil back, which means we will start another one. We're doing the same thing again. Let points there. Result, which will be a call of f on x. F is which f? Here, 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 here. This one. Same one as before. F is now that lambda of n, which we are applying to x, which is in this case 2. Looking at that code, it's going to do the same thing again, right? Because those base cases aren't yet hit, so we have plus memo fib n minus 1 is 1, and memo fib of n minus 2, which is 0. Oh, well, I guess we have to keep going then. So let's take this one here, which will be 2. And so we start another one of these. Memo fib points to E1. X is 2. Sorry, no, X is 1. And we get another let with a prev, which is a lookup into the table, which is still empty, so returns nil. Therefore, we create another frame of the sublet, which points back here, and a result, which is f on x. F on x in this case will be the same f. The x is 1, but we trigger a base case finally. Oh, thank God. So we get a result, 1. Now what happens? Oh, well, sort of lost track of what was going on here. So we get a result finally, which means we then continue on with an insert. Bang of X, result, and table. Here's table. Oh, no, sorry. Here's table over here. I already got it. Insert bang X result table. X is 1. Result is 1. So we insert that as an association between the key 1 and the value 1 into the table. Therefore, at step number 2 here, table becomes, no, I didn't want to write in that in orange, just the arrow. Star table star of association between 1 and 1, like that. I hope you see how this is now going to finish. Was that a yes?
Complete silence.
Right, so now we've done the insertion. We return the result. Where does that go? Wow. So that goes back up here to here. Is that right? No. To here. So now we have 1. Where's my orange chalk? We now continue on. Call number 3. Call number 3 does the same thing. Blast on through it. Memo fib. Up to E1. X is now 0. We create a let frame. That points back there. We have free nil, right? Because we do a lookup of X, which was 0, in table, which is here. There's no association, therefore we get nil back. Therefore we continue on down here. We get a result, again, of 1. Well, through the application of f on x and go through. Thank you. The alternate version, which then causes us to do another insert, because we have a new value. Insert bang x result and table. That then causes this to mutate to table with our new association between 0 and 0, which goes first or second. There we go. 2. That then gets returned here, here, which was back here, so we have a 1. We can now
following it back. I'm not.
There's these. I'm remembering on the substitution side here.
Okay.
It's not readily shown on the chain.
Okay.
So, thank you. 0 plus 1 is, now we can do this addition. That becomes 1, which is a result of this, which brings us back to x of 2 here.
But wait, don't we have to put that in our table?
Oh, yes, thank you. Right, so which brings us back to here. This is finally the result of this application. We now have a result here, and therefore we insert with x and result into table, which will be x here table, because it's the same table because of the frames. And, oops, I forgot to write that one down. That one was 3. And then the next step, it goes on to the head, table, star. What was the value? 0.0, 1.1. And which step is this? No, that is the one of, that's 1. That's the application of 1. Now, we continue onwards. So this gets returned back, which is this. And we get a value of, look me, what was it, 1. It's not so hard at this point. We're almost done. I'm out of board space, so I'm going to continue over there. But so we now call orange. This is 1, 2, 3, the 4th call. Memo fib on 1. Calling that is a new frame, which has memo fib. X is 1. Inside that is a let. This goes up to E4, or E1 rather. And inside that is prev. Here's the magic. We now do a lookup of X and table. X is 1. Table is this. There is an association. We succeed on the lookup. There's the return value 1. So this immediately gets bound to 1. We do not proceed. We do not generate any additional recursive calls. They're short-circuited. This comes back. You can see how quickly this returns. And we get, what was the value? 1. These two get added together. We get a 2 here, and this gets inserted. Note that there was no insert down there because we had a successful lookup here. So we did not do an insert. There was no need to do one.
It seems to me that the OR should return true rather than the actual value because it's going to get to...
It's going to return the actual value. That's the definition of OR.
Oh, okay.
It returns either nil or the value of the last expression,
Okay.
the first non-false expression. So where were we? We do an insert bang here of X and value and result into table, where X is 2 and X is 3, result is 2, and that causes this to now mutate, whoops, orange. This is step number 4, to mutate to table star of 3.2, 2.1, 0.0, 1.1. Close. And this gets returned 2, gets returned here, which is, lo and behold, the return value of this expression. Thank you. I would just not make it as a scheme interpreter. 2. So,
Faster than the iterative method.
if we had called memo fib of 3, we would have had to have computed memo fib of 2, memo fib of 1, memo fib of 0. And then the rest would have just happened as lookups. So we would have consed down the chain, or coded down the chain in essence, decrementing as we went along, as you saw in this gory detail. But then every subtree would be short-circuited. So we would only have to do each previous value exactly once. Anytime that we hit a previous value again through these 2 different branches, the secondary one would be already computed. Yep.
This table stays in state, so we can use it again later.
And this table stays there because of the binding here.
Well, it stays the state until the end of the memo fib.
Or, sorry, because of the binding here.
But as soon as we execute memo fib, it goes away.
No, it doesn't.
We have no way to...
It's part of memo fib. Memo fib is defined to be this procedure there, and the environment is that table. Whew. Okay, so that's in all its gory detail exactly how memoization is implemented in these relatively simple functions.
This is still,
Ah, come on!
this is still, because I assume looking up on the table is linear, so this is still n squared,
Yes.
while our iterative was
Yes.
n.
We can actually make our lookups be much faster. We can make them n log n
If they're ordered.
if they're ordered, or we can make it almost linear. So one of the things that complicates this diagram is, as you can see, the insistence on every time you have a let of creating a new frame. And if you're careful about that for nested lets like this, if you're careful about it, you can put them in the same frame, and it makes it a lot easier. But you have to be careful about doing that.
I mean, and you skipped 3/4 of the frames. I mean, you didn't do frames for the inserts, and that would be
Right, and I didn't do any of the frames for the table. Those were taken to be atomic. So it would have been right.
You have
Yes.
100 boxes by the time you were done.
Yes, which is why we didn't do that. Okay. Yes.
But this would have a really interesting application in distributed computing or distributed applications.
Very, very good observation. So you have, I mean, what we've done here is we have exposed now all of the computations that have to happen. In some sense, we've enumerated them, and we could, ideally, have different processors operating on each one of these. And this is the essence of how parallel computation happens. You have a problem that's composed of many, many small subproblems, and you distribute those small subproblems onto an array of different processors and hope that they're sufficiently independent that they can make some progress, some headway on the subproblems, and then combine them up in the end without too much difficulty. Yes?
But using the memorization system, haven't we made this process necessarily linear? We can only defer all of our processing until our table has been propagated to the point that we're caught up to
Yes.
our process.
Yes. Although you can, yes,
The recursive algorithm is much better.
yes, yes. Does everybody understand that? That's a subtle point that you'll get when you talk about.
You'd have to synchronize the tables, which would...
You'd have to synchronize the tables, and in fact, for this particular expression of the problem, the computation isn't going to actually be able to make much progress until you have the table initially filled in for the first n values. Although it will be able to, you'll be able to exploit the parallelism in that computation of the first n values. But after that, you're not really going to gain very much. Primarily, well, not as much as if you have full recursive definition without the delays.
You could also
This is a subtle point that, if anybody's interested, I'll talk to them afterwards about it.
you could also preset the beginning of the table. In a situation like this, we know some of these values and could
Yes.
start them in the table.
Yes, absolutely. Okay, so we are over time. Somebody's dead back there, I think. And I appreciate your indulgence in this hairy diagram.